could be applied to everything else. You could be a songwriter, turn your caffeine into songs. You could be an artist, turn your caffeine into masterpieces. Question is, what do you turn your caffeine into? Alright, so we got a lot of, we've had like a storm of nice ideas lately. And they all address this question, what is a derivative good for? Let me just mention a couple words about each one of these. It's been a storm of brilliant ideas. We had this amazing idea that made finding limits extremely elegant and easy. It was called the L'Hopital rule. As long as you had the right form, you could take the derivative on top and the bottom. That was very, very nice. Way better method than a lot of the other methods that we had. Then we had finding this tangent line, which makes it easy to approximate a lot of these functions using the line rather than the function, and get more or less good results using nothing but noodle power. And the idea of a derivative, we had the degree 1 sketch, which tells you upside down, uphill, downhill stuff. Second derivative tells you concavity. Sir Isaac Newton has this brilliant idea on how to solve equations. And of course, we had the very nice section last time on related rates. This one was so nice because it tells you that really every time you know how two quantities are related, V and H, or it could be I and R, or whatever, you slap a DDT on both sides and boom, you know how the related rates are related. I like that one a lot. Actually, I like all of them a lot. That's why I'm thinking this is really a parade of just brilliant ideas, nice uses of the derivative. And that puts us in a really good position to add a seventh application of derivatives. Okay? And in fact, we'll have a seventh and then an eighth, and then that we'll call this a chapter. This will be chapter 3. So we got a couple more really nice ideas. All right, so on with it. What are we doing today? Talk is cheap. Let's do it. So I had this idea that I'm going to invent something good. I'm going to invent something really good, something that puts a little swagger in people's walk and people's talk. Swagger. I looked this up in the dictionary. It had things like conceited, show off, arrogant, and I loved it. I said, hey, that's the word for me. So I wanted to make a little, I thought I would make an invention here. I'm going to make an invention called swagger juice, or a shot of swagger. And I was thinking that I could sell it in little cans like this. Well, maybe they're not so little. But the cans would come in 100 milliliters. And for those of you keeping track, that means 100 cubic centimeters. And it could last for 5 days. Hey, what about that? I see all these other things, energy drinks that say last for 5 hours. Forget that. I'm gonna make mine last for 5 days. For 5 days, you could put a swagger in your walk, a swagger in your talk, just by drinking one of these. Wouldn't that be nice? Of course, the only thing I had to decide was, hey, if I'm gonna package this nicely, and I'm gonna package it in shots of 100 milliliters, how should I shape the can? Should I shape it like this? Or should it really be a much thinner and longer can, kind of like this? Or should it be more of a flat can, kind of like the, let's see if we can find one, kind of like this kind of can, where it's really flat and not that very tall. They all could hold 100 milliliters. And this one could hold 100 milliliters, or the original one could hold 100 milliliters, but the shape might have something to do with other things I need to consider. For example, the surface area. The question is, which one? Suppose I focus on the following question. Suppose I'm a very concerned environmentalist, and I don't want to waste a lot of material, because not only is that expensive, but it's bad for the environment. Suppose I wanted to minimize the surface area, and all I cared about is minimizing the surface area. What would have to happen for me to compute what the best shape is? You guys understand the problem? We're going to sell swagger shots, and we're going to put them in a can. And we need to figure out what kind of can should we make them into. This kind of can, or this kind of can, or this kind of can. Which one would give us the best, the most optimal surface area for the can? That's the problem. And so you start to think about it, you can get pretty far just using common sense. You guys want to try that? Let's try and see how far we can get without any calculus. Let's leave the calculus on the side for a little bit, and let's use the power. Let's unleash the power of common sense, and think about this. Suppose we consider first the flat one. This is like a tuna can shape. And suppose I pick a big radius, for example, 6 centimeters. That would be pretty big. That's like a tuna can radius. And then I ask a simple question. If the radius is equal to 6 centimeters, how much surface area is being used? Okay, it's a very simple common sense question. What I'd have to do to answer that is I'd have to take this and break it up into pieces. I would have to take the top piece, which would be a circle, the bottom piece, which would also be a circle, and then the middle piece, which is the side, which you could cut and then turn into a strip, which would be the shape of a rectangle. Of course, to find this surface area, the area here for this piece would be given by the famous formula pi r square, which would be pi times 6 centimeters square, whatever. That would be 36 pi square centimeters. Okay? And then the bottom area would have to be the same, because the radius, of course, would also be 6 centimeters, and so the area here would be same as I just calculated, 36 pi square centimeters. Now I just have to calculate this one. Well, the length of it would be the circumference around the circle, because this has to wrap around the top. And so this would be 2 pi r as far as the length goes. And then I just have to figure out the height. How tall is it? Well, for that, again, common sense will take us a long way here. I have to figure out how tall is this piece. Given that the volume is equal to, we said 100 milliliters, and I know that volume on a shape like this, volume of a cylinder, is pi r square h, and so this must milliliters is the same thing. I can exchange those milliliters for cubic centimeters, right? So 100 cubic centimeters is equal to pi r square h, and I know the radius is 6, so 100 cubic centimeters is equal to pi times 6 centimeters squared times h. So therefore h, the height, would have to be 100 centimeters cubed divided by pi times 36 centimeters square. These centimeters would cancel those, or at least 2 of them would cancel those, and my answer would be 100 over pi 36 centimeters. Right? Nothing but common sense. Just figure out, you know the volume, you know the r is 6, you could figure out the h. Okay, so maybe we can pull out a little calculator. Let me see if this is the button for the calculator. Yes, it is. So I'm going to go with 100 divided by pi. Where is my pi? Times, well, I got to do 1 over 36. 1 divided by 36. That's the same thing. So I get that my height is 0.88. I'm going to say 0.8842. Okay? So this would be 0.8842 approximately. There you go. That's the height. So I go back to my finding of the surface area, and I get a total of, how much do we get here? 0.8842 on the height, and 2 pi r, that would be 2 times pi times 6 centimeters. By the way, this is centimeters. And so the area here, the area for this piece is equal to 2 pi r, that's the length, times the height, which is height, and that would give you a total of 12 pi, that's 6 times 2 is 12 pi centimeters, times 0.8842 centimeters for a total of, let's see, let's pull out our calculator here again. I'm doing that guy, whatever I had before, times 12 times pi for a grand total of 33.33 centimeters square. And then I would add it to this, which this top one was 36 times pi, so 36 times pi, that gives you 113.09. This one's 113.09. So a grand total of the total surface area, if I shape my can like this, the total surface area would be that times 2 plus, because I got two of them, plus this one in the middle, which was 33.3 centimeters, for a grand total of 259.49 centimeters square. So there we go. Back to the question. I want to package 100 milliliters of Swagger juice, and I want to do it if I choose a radius, if I choose a shape like this, if I choose a shape like this with 6 centimeters, I will get a total of 259.46 centimeters square. That's how much surface area I will need for the packaging. That's how much aluminum or cardboard or whatever I use. That's how much I will use, 259.46 centimeters square. Little squares like that. You think, okay, that's great. That was kind of fun if you're in algebra class, right? But this is Swagger juice. But we've got other options to consider. We'll say, hey, what if it was better to create the can this kind of shape, where you don't make a big radius, you make a small radius, say like 0.5 centimeters or something little like that. What would happen then? And so the shape then would look more or less like this. That's what it would look like, right? You got the top, you got the bottom, and you got this little square in the middle. And of course, the area on the top would be pi r square, the area on the bottom would be pi r square, and the area in the middle we say is 2 pi r. That's 2 pi r from there to there, and of course the height. So the 2 pi r times the height, that gives you this piece, and then the pi r square gives you that one, and another pi r square gives you the bottom one that you can't see right now. There you go. So alright, let's get to it. Talk is cheap. But by the way, I get tired of calculating this h. I'll do it one more time. What the hell? So let's do it again. So if the volume is equal to 100 centimeters cubic, and the volume is also known to be pi r square h, so that means 100 centimeters cubic is equal to pi r square times h. That means that h is equal to 100 centimeters cubic divided by pi times r squared. That means in this case, for this particular one, if I'm going with a radius of 0.5 centimeters, my height would have to be that. So I use my little calculator and I go, okay, I got 100 divided by pi, whatever that is, and I have to divide it by 0.5, so I divide it by 0.5. I have to divide by another 0.5 because that was 0.5 square. Gives me a total of a height should be 127. Come on, where are you? 127.32. See that? I hope I did that right. So then we go back to our formula here. Let's see our formula. So the height is equal to 127.32. And so therefore the total area is equal to, I'm going to go like this, 2 pi times r, which is 0.5. Forget about the units. The units will work out really, really nicely if you're keeping track of them. I won't for now. That's 2 pi rh. I'm following this recipe. 2 pi rh plus pi times r square plus another one. I should just multiply by 2, but I already wrote it this way. We'll go with that for now, but usually you just say 2 of these. And how much is that? Keep in mind that the way we had calculated earlier, If we do it this way, we get 259.46 centimeters square. It's an interesting question, just to think. Do you think we'll get more area out of the thin one, or smaller area? Well, we're about to find out. That would be, let me think. Let's see if we can do this. Let's clear everything. Now we already have the 127 in there. Might as well go with that. Multiply it times 0.5, then multiply it times 2, then multiply it times pi. All right, that times 0.5 times 2 times pi. And then we're going to add to that pi times 0.5 times 0.5. And then we're going to add to that. Well, I could just multiply that by 2, but again, I'm just going with this. So we're going to add to that pi r square. So that's pi times 0.5 times 0.5. That would be a total of 401.57 centimeters square. Think about that. So this tells you that if you go with this route, you're going to get about 401 centimeters cubic. This is not the most efficient shape for delivering a swagger shot. Yeah, if somebody designs it this way, they deserve to have no swagger in their walk, because this is such a bad design, at least from an ecological point of view. It's not a good design. So then that gets you thinking, okay, flatter is better, and so then you say, hey, maybe flatter is better. But then if you make it really, really flat, you're going to see that this number will go up even more. In fact, I thought it would be interesting to make a little chart. You know, I didn't want to keep doing this like an insect, one by one by one by one. So I put it on a spreadsheet. And still kind of like an insect, but maybe less of an insect. And I put it on there. And what I did is I put the volume here. Let me see if I can zoom you guys in. Can you see it? Let me see. Hopefully you can see it. I might be able to move it. Let me see if we can move it a little bit. So I have a little spreadsheet set up, and let me think. I put the radius here, and then here I put a little formula. If you can see the formula, maybe you can't see the formula, but you can if I move it. This formula calculates the height, so that's where I do the volume divided by pi r squared. That's exactly what I was doing earlier. I think here where I was calculating the height. To find the height, all you do is take the volume. Here, I'll do it here. Volume is equal to pi r squared h. So every time you've got the volume, you divide by pi times r times another r. That's r squared. That gives you the height. So I put that onto the spreadsheet. I said, hey, every time I want to find the volume, every time I want to find the height, that's this cell right here, all I do is take the volume, that's this cell, D10, and I divide by pi. And then I divide by the radius, that's this cell, and I divide by the radius again, and there it is. That gives me the height. For example, I think we had calculated this one. If I put 2 there, the height should be 7.95, which is wait. I think we did 6 right earlier. We did 6. See, I told you this point. Oh, don't tell me you can't see it. Can you see it? If you put 6 there, the thing's calculating, carrying out the calculation we did earlier, which was 0.8841, and it's giving you and then also did the surface area. I did some formula here for the surface area, which I had the 2 pi r square. That's the top and the bottom. That's 2 of them. Every pi r square, that's the top, times 2, that's the top and the bottom, plus 2 pi r, that's the length of that side, times the height, which is the H1 cell. Anyways, you could figure out your own way. I'm sure you guys are all smart enough to figure it out. I did a little insect stuff here to figure out a formula. That way I can just go like this. I can say, hey, if 6, let me get my little keyboard here. I said, hey, if 6 is good, why not go, if that's a big radius, right? 6, why not go for more? Why don't we go for 7? And look what happens when you plug in radius is 7. If we carried on the calculation, we would get that the height has to be 0.64. But look at the surface area. Oh my goodness, it's gone up to 336. So flatter is not always better. You end up with something worse. You say, well, maybe that was just a fluke. And then you go with 8. Suppose you make the radius 8 centimeters. So that's really, really flat. That would give you a height of 0.49 centimeters. That's like, 4 millimeters. And that would give you an area of 427. That means you're taking a lot of area on the top and on the bottom. And so on and so forth. So flatter is not always better. You say, okay, those were not that good. Maybe you got to go smaller. So you go to 2. Whoa. Let's undo that. So they say, hey, maybe I got to go with a radius of 2. If you go with a radius of 2, your height would be 7.95 and your area would be 1.25. That's really, really good. That surface area is way better than the other ones. It's much smaller. Say, okay, maybe I got to go smaller. So then you go to 1, and that gives you already something worse. And then if you go to 0.5, that's the one we just calculated for 1. Is that the one we calculated? Let's just see what we did using our little insect ideas. There it is. I told you. That's the one we just calculated for 1, and that's with 0.5 millimeter. That's a really thin one that has an incredibly thin top. So, what in the world is going on here? Really, really thin? This is what this tells you. Really, really, really thin is no good. Really, really, really flat is no good. Your area goes out way, way too big. It goes into 400s if you make this even thinner. Somewhere in between, there's got to be a perfect size, a perfect radius. Not 6 centimeters, not 7, not 8, not a half of a centimeter. There has to be a perfect that makes the surface area the smallest. We can even try to pinpoint it. We're still doing common sense. We're doing no calculus, okay? We're just using common sense. You could have done this in your algebra class. In fact, I'm going to do this on my next algebra class. Because there's no thinking going on, or other than just common sense. We're just looking at different radiuses. Okay, put radius 1, and then do all the little grunt work and carry out and find out what's the surface area. That's all we're doing. But we're serving a certain pattern. All right, I'm going to try to see if I can point you in the right direction. If you go with 1.0, look at the area. It's 2.6 or 206. If I go with 1.1, oh, it's 189. It's better. If I go with 1.2, it's 175. If I go with 2, oh, it's 125. It's even smaller. If I go with 2.2, ooh, that's 121. See, the idea is to get it as low as possible. Figure out the value. 2.3 is 120. That's even better. 2.4, 119. 2.5, 119. 2.6, 119. 2.7, 119. 2.8, 120. Uh-oh. See, now it started going up again. I bet you if I go with 2.9, 121. With 3, it goes to 123. With 4, it goes to 150. Look at the pattern here. I'm going to see if you guys can see the pattern or not. Maybe I can zoom in this thing. Let's make it 200%. Can you dig it? Look at that. So if you go with 1, if you make the radius 1, your surface area will be 206. For 1.1, it's 189. It's going down, 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 down. So these are better sizes. 2.5 centimeters is good. But then if you go a little beyond 2.7, guess what happens? It starts to go back up. As soon as you get to 2.9, 3, it starts to go back crazy, to the 400s. What does that tell you? It tells you that somewhere between, I can even tell you where between. Somewhere between 2.3 and 2.8, somewhere between there's got to be an optimal optimal surface area that's even less than 120 centimeters square. Can you dig it? Think about that. That's just using common sense. That's not even doing any calculus. Common sense says, hey, somewhere between here, there's got to be an optimal shape. And you can even graph it. You can even imagine a graph here. You can make a graph where you compare two things. Ready? We can compare, let's make a little line here. Let's make a line here. Imagine a graph of the function here. Imagine that you start thinking, hey, what if I have a really, really small can like this? If I have a small can like that, and I make the radius say 0.5, well, I get up to the surface area. I'm going to call this A for area. It would be 400. That's not good. If I make it about 2 centimeters, oh, it gets down to about 120. That's pretty good. If I get it to 2.5, which is a little smaller, a little wider, it gets it to about 119. So it gets it around there. If I get it up to 6, I'm back up to 200. If I get it to 7, I'm back to 400. You can imagine that the graph probably looks like this. If you were to plot the radius, this is the radius axis, the radius versus the area, as you move the radius really, really, really small, your area goes up. As you move the radius really, really large, the area also goes up. But somewhere in there, somewhere in here, this is the really, really, really flat cans. They're no good, man. They give you a large area. But somewhere between these type of cans, there's an optimal shape. There's a point where you reach the absolute smallest possible surface area. That, my friends, that's what we call optimizing. And it has nothing to do with calculus so far. That's what we want to do. The idea is huge. It's so huge. I can't even tell you how huge. I mean, imagine if you're building billions and billions of cans. One little tweak could save you 1 centimeter of aluminum. That could be, billions and billions of resources. But it's even more huge than that. I mean, you could maximize, all sorts of functions. Suppose you're a company, you want to maximize profits. Anyways, all this stuff we found out was just using a little spreadsheet and some common sense. Now, let me tell you the calculus part of it. The calculus part of it is just one little idea. One essential idea. And it solves the problem beautifully. That's all it takes. So many things in life are solved by just one little spark of creativity. Solves the whole problem entirely. That's the case in this problem as well. It's time to think big. This part I call, this is the part where we call thinking big and thinking brilliantly, thinking like a human, no longer like an insect. This spreadsheet stuff, that's alright, but we gotta go bigger than that. And all it takes is just one brilliant idea. Here's a brilliant idea. You ready? Wherever the minimum point is, suppose it's right here. There's one key ingredient or one specially important clue that you know about this point using derivatives, and that's the key that solves the whole problem. Imagine a tangent slope right there. If in fact it's a tangent slope, that means that, and if it's the bottom of the little valley, do you think the slope would be going up or down, or neither? The fact that it bottoms out here would tell you that as you zoom in here, it would look flat. It would have to look flat. That right there, that's the key observation that solves the entire problem brilliantly. That at that point, whatever the point this is, we'll call it C because we don't know where it is. At that point, the key observation is that the derivative must be equal to 0. Either that or the derivative must not exist. If it's a weird function that jumps or does other kinds of weird things. But if it's a nice continuous one that's differentiable, its derivative right there, it's got to flat out. Otherwise, it wouldn't be the value. If it kept going down, then you wouldn't expect this to be 0. It would be tilted. But if it goes down and comes back up, the rate of change at that point must be 0. The slope must be 0. That right there, as simple as it sounds, one little sentence, that's what solves the problem. And that's it. And then all you got to do now is just apply exactly this idea to all these optimization problems, and you're done. As easy as it sounds, that's all it takes. Want to try it? Let me give you some guidelines, and then we'll try the same problem using the guidelines, and then we'll try a couple more, and that will be it. You'll be a master of optimization. Okay. So here's a little outline that will always help you or guide you into the right direction. If you follow this procedure, I think every time you will succeed finding the optimized value of these functions. First of all, you got to read the problem, read it till you figure out what are you trying to maximize. As in our case, we were trying. By the way, this could be maximize or minimize. Really, I should say optimize what. In our example, we were optimizing surface area. Okay, the next step, figure out a formula for whatever that is. Since we were doing surface area, we need to find a formula for surface area. Once you've got that formula, you got to eliminate all variables but one. And then you find critical points. Remember, critical points are points where the derivative is 0 or doesn't exist. That's exactly the points where you have either peaks or valleys. That's exactly the point. If you have a peak, the derivative must be 0, or if you have a valley, the derivative must be 0. If it's a maximizing problem, it'll look like this. If it's a minimizing problem, it'll look like that. Either way, you look for, or they don't exist. Either way, you look for critical points. And then you test each one. The reason you test each one is because you want to make sure that if you're looking for a max, you get a max. If you're looking for a min, you get a min. To test it means to check and see. Maybe you can check concavity. If it's concave down, then you know it's a max. Or maybe you could check concavity. If it's concave up, then you know this has to be a min. Or there's other ways you can check, but you want to check it. And every once in a while, you got critical points that are neither one. Maybe it goes like this and it flats out and then it keeps going like that. That could happen too, where the tangent slope is 0, but it was neither a max or a min. These are called relative max or relative mins. And so that's why the fifth step is important. Once you've got your critical points, these are sort of your candidates. You've got to do a little bit more testing to make sure you've got the right one. Clear? Let's try our little sequence of steps on exactly this problem and see how it would look like without this spreadsheet, without any of that. Just doing the problem.